Yes, so in this talk, I try to, present to you a bigger picture of how I see the compute continuum, engineering the new fabric of IoT, edge, fog, and cloud. And this is essentially a composition of multiple years of work spiced with the wisdom of a guy who lost most of his hair. And I'm trying to put these things together into perspective. And what I really would like to do is to propose to you kind of a research agenda, how we can move forward together, because this is not something that one person or one team can do. Mastering this field of a compute continuum, as I put it, is really a big task at hand. And together we should aim at this. And I think this is exactly the right community that should address this. So I always like to begin with an observation, namely that we are living in a world where we are kind of seeing an evolution of smartness, under quotes. What is interesting is that if we look at it from a higher level of perspective, we can see that people, software services, and the Internet of Things are being put together into new types of systems, which I call elastic systems, which also support elastic processes. And what is really interesting about this is that in the past, people were typically outside the systems. They were interacting with the system, but they were not integral part of a system. The Internet of Things was many years ago, a couple of years ago, not too many actually, even also outside the concern of typical computer scientists. It was mainly the domain of electrical engineers, right? So in other words, computer scientists were mainly concerned with software services in a more modern terminology. People outside, things outside, but this is changing. We are seeing now systems where in different walks of life, like smart homes and smart buildings and e-health networks, in governmental networks, in all kinds of administrations, transportation networks, energy networks, that we see people, software services, and things being put together, composed, weaved together, and creating new types of systems. So in other words, all these systems share this common base that they have the composition of these three to a different degree. Some systems have more people, some have more things, some have more services and things, etc. So the idea really is, the challenge really is, how can we build systems, design them, monitor them, govern them, all of, the whole stack that are of systems which are composed out of these building blocks. And this is quite a challenge, because if you look at it now from how the history was, we have systems which are supporting people, like social media systems, collaboration systems, which are really completely decoupled from the other systems. We have the worlds of Facebooks and emails, etc. We have the worlds of IoTs connected to the cloud, and we have the world of software services that we know from enterprise computing, for example. But when we look at the picture today as it is presenting itself, we can say basically that everything is connected with each other, because ultimately what we want to do is we want to be able to delegate some things from a software to a person or to a team of people, or from getting the data from IoT, doing something with it on a people side and delegating it to software services, and back and forth, etc. So everything is connected with each other. So when everything is connected with each other, a good analogy is basically nature itself. We have an ecosystem, so to speak. And in nature, I want to give you one example, the marine ecosystem, which is a complex system, and it has network dependencies, it has intrinsic behavior, and it adapts itself. In the marine ecosystem case, we have the sun, we have the birds, we have the water, we have the rocks, the animals, etc. All of these different actors and components are being put together in the marine ecosystem, right? And there are these yellow arrows in this picture you can see, depicting the relationship that these actors have with each other. And when we look at ecosystems, we are knowledgeable about how to treat such an ecosystem. So an ecosystem is robust, it is resilient, so it has stability in the presence of disruption. It has this robustness not because it is solid, quite the opposite. It is robust because it is kind of elastic. I will talk about what I mean with elastic in the next minutes. It has measures of health, so we can say something about diversity, population trends, other key indicators. And what is extremely exciting, it is that it has built-in coherence as well. Coherence in a sense that it is basically somehow glued together. It has a purpose, it has a direction. And it is to some degree resisting entropy. Entropy as a measure of disorganization. So we can say that it is somehow having the property of syntropy, the opposite of entropy. So it is being put together, it remains quite resilient and strong. These are properties which I would suggest are interesting for us to emulate in the world of systems that we are designing. What is a good example for such an ecosystem? I think that when we look at the ecosystem for distributed systems, our sun, fish, rock, and birds are basically translated to compute power, networking, storage, etc., right? And a good example is a smart city. A smart city basically has the things, all the sensors that are there, air, fire, traffic, video surveillance, etc. We have the software services which are basically building applications utilizing these sensors for disaster management, traffic control, crowd management, water management, what have you. We have us, the people, running around in these cities, leaving traces of data, right? So basically, these are the building blocks of the ecosystems that we are talking about, where everything is provided as a service. And the service-oriented paradigm basically gave us cloud computing. It allowed us to have these necessary abstractions so that we are able to move forward as a paradigm in our field. Now, in the last couple of years, however, we have developed a cloud-centric perspective. The cloud-centric perspective essentially says that the cloud is the center of the, let's say, systems universe. Everything is connected to the cloud. So the things, the edge devices, everything is connected to the cloud. Without the cloud, nothing can actually happen. The other perspective would be the internet-centric perspective, which basically says, no, the cloud is just one actor in this play. There is the internet as the foundational layer, the topology, the infrastructure, the behavior, everything is based on the internet. We have things, we have the cloud, we have the edge devices connecting via the internet. So that would be the internet-centric perspective, which brings with it that it is more autonomous. It can have intelligence, which is distributed and decentralized. Whereas cloud computing, even if many people would say that it's kind of coming out of the distributed systems world, essentially, if you look deeper, it led us to a centralized world. Sure, we have multiple data centers, but essentially the very paradigm of cloud centricity brought more of centralization with it. And for me, as a distributed systems person, I'm more excited about distribution and decentralization. So that's why I naturally gravitated now more to look into the edge. So this pendulum of centralization and decentralization is essentially swinging back and forth every 10 years or so. And this is where we are now, at the tipping point of this moving back to the decentralization and distribution. I want to bring an example for a dynamic compute continuum infrastructure, which we really require, especially now in the ages of pandemic. When you look at the type of questions we would like to ask of our systems, it's extremely difficult to actually ask questions such as, how is the well-being of a certain population or a certain region, or even one street or one part of a city, and combine that information with data from government services, hospital services, even building management, etc. So these horizontal and vertical separation in silos that we have done in the last 50 years led to the situation that we have now, where we have, for example, a pandemic, where we have the problem of actually putting these things together. So I mean that, for example, when we look at the health and the well-being of people, we have to use simulations. Those simulations have to be fed with offline data from insurances or whatever. And we are not able to actually combine mobility data with healthcare data from hospitals, etc., etc. This is just one little example illustrating the problem that we face today, that we are not really very good in answering new questions. And this is basically my argument why I would suggest that we need to be able to build dynamic compute continuum infrastructures. And here, I think we need to improve, because if we look at it purely from a cloud-centric perspective, everything has to be transmitted to the cloud before it can make sense. This is somewhat problematic. So one observation I would like here to begin with is that there are new families of applications that require real-time location-based access to data from the environment at different levels of fidelity. So this location-based or context-based, location is one form of a context, data from the environment is definitely one thing that the Internet of Things revolution or evolution brought with it. The different levels of fidelity is quite exciting because it means that we are introducing a notion of good enough here in the world of systems. In other words, when you're creating an application which is, let's say, take the temperature of a city, for example, or other way around, let's say you're building an application which has to take a temperature of one particular room, it is not good enough to have the data of the temperature of the city, right? The fidelity is simply different, the granularity is different. Secondly, we increasingly have compute and storage resources which are in closer proximity to data producers and consumers. So it's simply a question of the current times that we have edge resources which are closer to the edges of the network, which are used and utilized as compute and storage resources. And we have to use them appropriately. And the question is, how do we do that? Now, when we look at the continuum, the compute continuum of what I'm speaking here, I look at the question of IoT, edge, fog, and cloud as a continuum. So if you look at the left-hand side, we have the IoT world with different properties. It has low reliability, it's highly volatile, it's mobile, small form factor, battery constraints, etc. And interestingly, it is provided and controlled by users, in some cases by service providers. As we move to the right, the control changes a bit. So we have edge devices, which might be the edges of the network, like telco operator equipment, but not necessarily, could also be provided by individuals or by corporations, or even by governmental agencies, for example, responsible for one building or a block of buildings. As we move to the right, what I call the fog computing basically could be telco operated base stations, which are monitoring, managing, governing whole regions of a city. And finally to the cloud, which is, as we all know, providing, under quotes, unlimited compute and storage, the whole full spectrum of everything that we are dealing with in our work, right? So the question basically becomes for us as researchers, but also for industry, is how do we actually utilize this whole zoo basically of equipment that we have, from the IoT to the edge, to the fog, to the cloud. If we abstract away from that, you could say that it's we have different tiers. And the question is, how do we horizontally or vertically deal with that, right? So do we distribute stuff horizontally? Do we distribute computing, storage, etc., vertically? Well, the answer would be probably both, right? We require how to do that. And my underlying pitch here is that we should not do that by hand. This compute continuum, horizontally and vertically, is pretty diverse. So it goes from data centers, represented here on the left-hand side, to mini servers, to micro clouds with Raspberry Pis. So it's a really literally a zoo of different devices. And the question is, even specialized compute platforms such as these AI cards that we have from different vendors, which provide AI functionality already on the hardware on these little devices. The question becomes, is it possible to write the software once and run it everywhere? So the underlying assumption somehow is it possible to push that intelligence into the infrastructure itself, into what I call the compute continuum, so that we can enable all sorts of application type scenarios like city scale edge computing with all these different edge devices that are out there. Some represented here in this picture, where everything is connected with each other. So my underlying assumption is, yes, we have to deal with those. And one way to address that is by utilizing software intensive edge systems, where we totally rethink the design and operation of those environments, because we have to deal with fundamentally conflicting system factors. So we have to basically constantly trade off between different factors, such as latency, which is inherent in this division of cloud and IoT, and that affects timeliness and performance of a system. So in other words, depending on the application, we have different tolerance regarding latency. Augmented reality, VR applications have a completely different aspect regarding latency, like gaming, etc., compared to enterprise applications. Then secondly, the safety and security is concerned with computation as an edge resource. So we have to provide that. We have locality and mobility, dealing with privacy, configuration of software, and evolution of software. So these things are best treated when we look at it from a software intensive side, not from a hardware side, right? So the question becomes, which characteristics of edge computing systems should be abstracted as first-class citizens into the underpinning model of how we design such systems, which go across the IoT edge for cloud continuum? How do we do that? What I would suggest is to look at some hypotheses. What could we actually, how could we deal with that? So different aspects would be proximity or context, capabilities of these systems, even energy consumption could be one way to structure the research, how we could distribute the load of these different aspects. What I suggest here in this talk is to look at what I call elastic diffusion. And elastic diffusion is basically, it sounds kind of interesting to me at least, because it has two fundamentally interesting principles, which we also find in these ecosystems that I was trying to emulate right from the beginning. The first one, elasticity. I think that elasticity brings with it the feature of resilience. So we know elasticity from physics. It's a property of returning to an initial form or a state following some deformation. So in other words, you put force on a material, it stretches. If you take away that stress, it goes back to its initial form. So then you would say, isn't elasticity basically everything that we are talking about constantly in the cloud world? Well, yes and no, I think. I would suggest that mainly when we talk about elasticity in the cloud context, we are actually still talking about scalability. And the reason is that basically we are still building the systems for the worst case, with the worst case in mind. What I would suggest is to consider taking two other dimensions into consideration as well. Because it's not only the resources that we would add or remove, it's actually much richer if we decide to go that route. So what I suggest is that elastic computing can be more than scalability. We can look at it from three dimensions. One is the question of resource elasticity, adding, removing resources. Those resources can be hardware, but actually could also be people. But that's a completely different story. I don't go into that because it would be too long. So adding, removing resources is one aspect. The other aspects are quality elasticity, like non-functional issues such as quality of the data input and the data output that can be changing depending on the application, and the cost elasticity. So in other words, what I'm saying here is that when we create systems, we are not building them only for the worst case. We would like to have an application which basically breathes with the system world and the applications. So we have a certain number of resources that we are able to use, considering that it delivers a certain quality aspects and considering that it does not cost more than X amount of dollars, right? This is what we would like to be able to specify. However, this is extremely difficult to do today. We are able to specify it only with resources mostly, but we are not able to actually attach elasticity requirements or specifications to these different services. So some years ago, we started to look into this question. How is it possible to attach these elasticity requirements into different levels of abstractions? Into cloud level services where we don't know what's behind it, so it's a black box, or service units, or even code where we don't have service abstractions. And we created a language called Sybil, which allows us to describe primitives which basically create constraints, define constraints, and then define a strategy what to do when constraints are met or not met, etc. You can see some examples here on the left-hand side as an example of these different levels of abstractions. And what we did in this project was basically doing the reshuffling of service deployment on cloud virtual machines represented by these puzzle pieces in green in this picture. And when constraints are not met, represented by red dots, the system itself, because it is monitoring these constraints, reshuffles the deployment as such that these constraints are met. So that's the basic idea. And the reasoning behind this is that we can then come up with an elasticity model, not only for cloud services, but also for edge services, which allows us basically to look at an application life cycle as it moves from the left to the right over time. And the application is represented by this triangle: resource, quality, and cost. And we look at it from two aspects. One is the elasticity space, where we can say, is the application actually within this elasticity behavior as we have defined it in these constraints above, or from a specific point of view. So I can characterize elasticity behavior from a particular view of, let's say, cost. I can look at the trajectory of the cost over time of a particular application in my infrastructure. And what we argue is that these functions basically are very helpful for the engineer to design and basically then also to monitor and see if everything is actually up to the task and actually where exactly the money is being lost or the quality could be improved, etc., etc. So that's the idea. So we have done this on the cloud. We are doing it now on the edge as well. And the goal is basically to roll this out from the edge to the fog to the cloud. The whole continuum is able to basically look at this from an ecosystem perspective and change the topology of the application infrastructure, as well as the dynamic behavior of what is going on inside the application. The second keyword was diffusion. So elasticity is a property we know from physics. Diffusion, I would like to take the term osmotic here, which we called osmotic computing. And osmosis is a principle of chemistry. It represents the diffusion of molecules from higher to a lower concentration. So the idea is quite simple. If there is high pressure, the molecules go to the lower concentration. And similarly, what we would like to achieve is that these microservices that we develop, all of us, are able to go where they are needed in the infrastructure. The infrastructure being the whole spectrum from IoT, edge, fog, and cloud. Currently, we have to be pretty well knowledgeable about where to deploy our services. The argument here is that this is fundamentally not very helpful for the future to come, because these infrastructure requirements are constantly changing. And this is why we suggest to bring in this concept of osmosis. We've created an international lab under the umbrella of osmotic.org, where a couple of research labs contribute open source tooling, research papers, etc., to actually follow this idea. So all of this is quite detailed in several papers. I don't want to go into this because I want to give to you this very high level ideas with some conceptual framework that you are able to actually understand what I'm talking about here. So this elasticity and this diffusion, so elastic diffusion, I think, are two key principles for us to build compute continuum systems for the future. Now, the second part of this talk is basically looking into the question of the edge and the intelligence regarding the edge. because this is somewhat a new phenomenon, right? So this computational fabric that we are managing today is predominantly cloud-based, right? So my main argument was that we should basically move now more to the edges of the network so that these resources that we have all over the place in the network are becoming part of this infrastructure. When they become part of this infrastructure, this means that we have to have intelligent operations and their mechanisms due to the scale of this infrastructure as well. Secondly, this computational fabric requires some automated AI application lifecycle, even down to the edge as well. And this is what I'm talking about in the rest of this presentation. How do we deal with the edge and the question of AI related to this edge? So this fabric for edge intelligence basically has three properties. The first one is looking at the sensor data as a service. So we have a large number and dynamic and mobile nature of pops up of sensor data and all these quality of service requirements, etc. However, currently everything is still pretty much centralized messaging services like the AWS IoT, Microsoft Azure IoT Hub, etc., where everything needs to actually be shifted towards a governance in a distributed and decentralized sensing infrastructure. That's one part. Secondly, these edge computer networks increasingly come with modular AI capabilities. What I have shown you in the beginning, all these different hardware devices come out now with new AI accelerator cards for these edge devices. Even smaller IoT devices come out with AI built into the hardware. And thirdly, the question is, of course, how can we build intelligent orchestration mechanisms for these decentralized and distributed infrastructures? And these can be very simple, like the picture here depicted in this little slide, where we have general purpose computing infrastructure like these Raspberry Pis that we have, and embedded AI cards on top of it, and basically looking at the AI lifecycle of processing, training, compressing, validating, deploying. And we've built a middleware, for example, to distribute the load on these different parts of the infrastructure, depending on the energy consumption. So these are just some little Mickey Mouse examples represented here, but I think you get the idea. So is it possible then also to distribute these AI lifecycle tasks across these different parts of the infrastructure? When we come to this distribution of the infrastructure, learning becomes a very important aspect. And since, I don't know, 8 years or so, we have federated learning in distributed systems, predominantly pushed by Google, where we have training on data directly on remote devices without actually revealing the data themselves, sending the outcome of this local training to servers and to aggregate them into global models and then making those models available to these devices. That's pretty exciting, and we all use that all the time in mobile devices for next word prediction, for face detection, voice recognition, etc., but also for organizations such as in hospitals, where they use that data, but they don't want to expose them, or also for bigger scale applications in environment, transportation, smart homes, etc. So we all use that all the time. However, not everywhere, because there are many research challenges at hand. Some of them are listed here. So we have the question of device recruitment strategies. So in other words, which subset of these devices do we actually assign learning tasks at any given round? We have the problem of volatility. These devices can appear, disappear at any point in time. We have the problem of asynchrony. So these algorithms face challenges when end devices don't submit their data in a timely manner. Can lead to bias as well. So we have non-independent and identically distributed data. Leads to inaccuracies. We have the heterogeneity in the volume of training data per device. So if one device contributes more, leads to a biased model, similar to if you have a team meeting, you have 10 people and the same 3 people talk all the time. Clearly you have a biased outcome because the other people are not heard. And the same is true in the machine world, right? We have to prevent privacy leaks. So some private information may be inferred even if the device is not transmitting the actual data. We have incentives to misbehave. In other words, why should I waste my battery when I can let others do all the work? So there are plenty of research challenges where we are basically all in this together at all the time, multiple communities, in fact, not only our community which is present in this presentation. So we created a research roadmap where we look at the question of edge intelligence and looking at the question of confluence of edge computing and AI. And we address that from the question, or the perspective rather, of the end user. So we approach that problem from the quality of experience level. So what does the user actually experience? And we discovered that there are 5 criteria what the user experiences. The first one, performance, of course, because the ratio of computational offloading is clearly showing itself in the performance of the overall system. That's what the user experiences. Secondly, the cost. So the cost of computation, the cost of communication, and the cost of energy. Thirdly, privacy and security. So federated learning plays into this here. So aggregating local machine models from distributed edge devices becomes an issue. Efficiency. We want to have excellent performance with very low overhead. So is it possible to do model compression, to do conditional computation, and reliability of the overall system? So that relates to the model upload, to the download, and the wireless network congestion. So here already you see that we are going to different levels of research communities, from the network to AI and to even, if you like, to lower levels of protocols. And these quality of experience then can be mapped to 2 set of questions, research roadmaps in themselves, basically. One is AI for the edge, and the other one is AI on the edge, which I will discuss right now. So for AI for the edge, we have 3 main questions regarding the topology, like edge orchestration and coordination with small base stations, or utilizing unmanned aerial vehicles and access points. Secondly, the content. So we have lightweight service frameworks for quality of service aware services, for example, on mobile devices, and services. So computation offloading, user profile migration across this whole continuum and mobility management. There are grand challenges for this AI for edge. So one is related to the question of the model establishment, so restraining the optimization model. The second one is concerned with algorithm development. So the selection of which edge device should be responsible for the deployment and execution in such an online manner is key. So state-of-the-art formulates that as a combinatorial and NP-hard optimization problem with a high complexity. And thirdly, the trade-off between optimality and efficiency. In other words, when is something also good enough? We have to create trade-off models for that. The other AI part is the AI on the edge. This one is concerned with data availability. So there is this challenge of lack of availability and usability of the raw training data for model training and inference. We have the problem of a bias of raw data from various end and user mobile devices. Secondly, the problem of model selection. So the state of the art requires a selection of a need to be trained AI model, and that has challenges in this setting, right? What is the threshold of learning accuracy and scale of AI models for quick deployment and delivery? And what is the selection of the right probe training network and accelerator architectures under such limited resources? And finally, the coordination mechanism. What is the coordination between these heterogeneous edge devices, the cloud, all these middlewares and APIs in between? Quite complex. And finally, to even add more to the drama of all of this, it is the question of managing the AI lifecycle. All of these typical AI lifecycle tasks of pre-processing data, training, evaluating, deploying, model creation, monitoring, etc. All of this is not only on the cloud, as I'm arguing here, but is and can and should be actually also distributed across this continuum of edge, fog, and cloud compute infrastructure. That brings with it a multitude of problems. Some of them are summarized here in our paper here, published actually in IC2E in 2019. Here, you can see in this table a summary basically of the AI operations workflows where we look at C2C means cloud to cloud, C2E means cloud to edge to cloud, and edge to edge characteristics and research questions regarding data characteristics, model characteristics, the enabling technologies, and some use cases that are used. I don't have time to go into this in detail because we want to look into this bigger picture in this presentation, where we can see that actually there are many, many interesting research questions along the line of AI operation workflows as well, because that is distributed across this continuum. So this brings me to the conclusion, namely that there are 3 points I would like you to take home. One is that we look at this as a computing continuum, meaning that there is an infrastructure outlook here. We have IoT, we have edge, we have fog, and we have cloud. And it's basically the question of all of these together. It's not just everything has to go on the cloud, because simply it is not working anymore. We have multiple of application types which require a different perspective of this. And ultimately, we don't want to create infrastructures always for particular types of applications. So what I'm advocating here is that we have to create an edge intelligence fabric, which is following this ecosystem understanding. And of course, as an ecosystem understanding, it requires novel mechanisms, novel paradigms to actually deal with this complete compute continuum. And finally, I presented to you our proposal for the differentiation between AI for the edge and AI on the edge. And I tried to kind of summarize a couple of their research challenges, which I think are very rich for this community to be involved with. And with that, I want to thank you very much for your attention, and we go into the Q&A. Thanks very much.